Good morning, respected judges and everyone present. We are Team 1 Innovators, and our problem statement is Sign Language Capture and Illustration System with Sensor Integration. Our problem ID is 25247 under the miscellaneous theme. Our aim is to bridge the communication gap between the deaf community and the hearing world using a smart, variable, and intelligent system. Now, if we talk about a problem background, millions of people in India depend on Indian Sign Language or ISL to communicate. But unfortunately, most of the population doesn't understand it. This creates daily challenges in education, workplaces, hospitals, and social interaction. Even more difficult is the case of illiterate users who cannot depend on text or speech output. So, we need a system that can translate sign language into readable, audible, and visual formats accessible to everyone. Now, for our solution. Our solution is a sign language capture and illustration system, a smart glove integrated with sensors connected to a mobile app powered by machine learning. The system recognizes IASL gestures in real time and converts them into text, speech, and animation. It can even optionally fuse with a camera to detect facial expression and grammar, making the interpretation more natural and accurate. Now, our methodology. Our methodology follows 5 clear stages. Capture motion data. The glove is embedded with a flex sensor and an IMU that detect finger bending and hand orientation. Stream data. This data is sent via ESP32 Bluetooth Low Energy to our mobile app in real time. ML recognition. A machine learning model trained on Indian Sign Language database identifies each sign or alphabet. Output translation. The recognized sign is instantly displayed as text, speech, and animated gesture. Optional camera fusion. For advanced user, the camera captures facial grammar and emotion, improving context understanding. Now, if we talk about our technical stack, our system has 4 major components: hardware, backend, AI ML layer, and front end. In hardware, we have flex sensor, IMU, and ESP32 microcontroller in a rechargeable glove. Backend handles data preprocessing and storage using Firebase and SQLite. AI and ML layer built using Python, TensorFlow Lite, and PyTorch Mobile optimized with quantization and pruning for real time performance. Front end, an accessible Android app developed in React Native or Flutter, designed with icons and vibration feedback for illiterate users. Together, this stack ensures smooth communication between gloves, model, and user interface. Now, for feasibility and viability. Our minimum viable product for hackathon includes recognition of ISL alphabets and 30 to 50 common vocabulary signs, low cost glove build for around 2000 to 3000 using easily available components, efficient ML model optimized for mobile devices and ESP32. We have also identified potential challenges like limited ISL dataset, censoring calibration issue, and hand size variation. To overcome them, we use custom gloves dataset, a calibration wizard, and incremental vocabulary scaling. Now, For our system illustration, to be more precise, this diagram represents our system flow. From motion detection, data would stream. Further, that stream data would be recognized by our ML product and would give us real time output. Each step is modular, making the system scalable for future upgrades like sentence recognition or gesture based learning. Impacts and benefits. Our project has four layers of impacts: social, educational, economy, and scalability. In social, it empowers the deaf and hard of hearing community to communicate freely. Educational, act as a learning tool to teach ISL to beginners. Economic, open up better jobs and communication opportunities for hearing impaired. Scalability, the system can be opted nationwide and integrated into school, hospital, and public service apps. Primary beneficiaries include deaf individuals, educators, healthcare staff, NGOs, and accessibility programs. By future scope. In the future, we plan to expand vocabulary to full ISL sentences, add bidirectional translation from speech to text to sign animation, incorporate cloud based personalization for each user signing style, build a nationwide ISL learning platform integrated with our glove system. These are the references that we took for making of this project. To conclude, our innovation is not just a device, but a bridge of understanding between the hearing and the non-hearing worlds. We combine hardware precision, AI intelligence, and human empathy into a single scalable system. Thank you. We are Team One Innovators and we are ready to demonstrate how technology can truly speak the language of inclusion. Gesture 1X is a smart variable designed to recognize and translate Indian Sign Language gestures into text and speech instantly, helping bridge communication gap for the hearing and speech impaired. It uses advanced machine learning and sensor fusion to support over 100 gestures and delivers results with 95% accuracy and response in less than 100 milliseconds, making real-time conversations smooth and accessible. It is a demo app. Further, the glove detects hand gestures using embedded motion and flex sensor, then transmit the data to a mobile app. The app processes these signals through a trained model and converts them into speech and text in real time. This allows sign language users to communicate effortlessly with non-signers, promoting inclusion, accessibility, and integration. In short, it is technology giving voice to the unheard.
Good morning. Hello, please.
Why do 70% of sign recognition systems fail in real-time settings? Because they rely on a single sensor stream for input and heavy cloud compute for processing. Our glove fixes that with on-device edge intelligence and multi-sensor fusion. This sensor-embedded glove uses multiple sensors to capture movement. Flex sensors measure precise finger bending in each finger. An MPU 6052 IMU captures motion and inertial data. It tracks hand orientation in 3D space and wrist motion. An ESP32 streams sensor data over BLE to a web app. The web app pre-processing filters and removes noise and normalizes readings. Python-trained models run on-device for low-latency inference using TensorFlow. Light-optimized models for mobile inference, or PyTorch. Mobile for edge deployment. Sensor fusion combines all sensor inputs for higher accuracy. Pruning reduces model size and removes redundant weights. Quantization lowers precision to speed inference and reduce memory. Together they keep it real-time on the edge. Optionally, MediaPipe Holistic Camera adds facial grammar signals. Outputs render in a React.js web app interface, as on-screen text captions, as synthesized speech output, as animated avatars that mimic signing, as icons and visual cues, and vibration haptics for accessibility. User progress syncs to Firebase cloud storage with local SQLite for offline learning and scaling. The promise: sign language tech that's fast, accurate in recognition and actually usable in the wild.